So today we'll continue with the review needed to better understand chapter 3. And yesterday we concluded with foliations, which I was surprised you've never seen before, but I don't think they will be too relevant later. But I think it's good to know that foliation that the distributions correspond to foliations when they are involutive. So now we will see something which I believe you did see before, but I hope that the way we'll see it will be a bit different than how you've seen it before. So we'll talk about the exterior derivative. This means just the differential operator, and the D. So we begin by defining lambda P of M as simply the pth exterior product of the cotangent bundle of M. Okay, so we know what's the cotangent bundle and we know what it means to take the external P power of it. We simply rename it like this. So this is the vector bundle. Of differential P forms on M. And we write omega MP for the set of smooth sections of this bundle. Okay, so this represents the set of all possible P forms. Yeah? So smooth P forms, so sections of this bundle. So usually when we have a bundle and we have sections of this bundle, we try to just look at them in local charts to have a bit better hand-on understanding of what's happening. So in a local chart, U contained in M with coordinates x1, xn, then we know that if we take the x1, the xn is a subset of the M restricted to U, this is a local basis. Yeah, so we remember what this means. It means that this U is diffeomorphic to some open subset of Rn. And on Rn, we have this standard coordinate derivations, and we just import them via the chart, via the local chart, because it's a diffeomorphism. But what we care about is the cotangent bundle. So we can look at the dual basis. Its dual basis is denoted by dx1, dxn. Now this is going to be a basis, a local basis of the cotangent bundle to U. And of course, it satisfies the usual dual basis conditions. Yeah, so this is the Kronecker delta, 1 if these are the same, 0 otherwise. And we also saw back when we defined this and when we defined the differential on functions, that this dxn is, yes, it is a symbol that represents the dual of this, but it's also the differential of the function xn, if you think about it that way. But we'll see it again. In fact, recall that if we take a smooth function, smooth function on U, then its differential is a section of this M U. Yeah. In particular, if we have a vector, tangent vector at the point M, sorry, at the point P in our open set, then if we apply the xj to V, so and in this way we're thinking, you know, this dxj as one of the symbols here, and we apply to V, then what you get is V applied to xj, and now we think xj as the function xj that takes a point P, which has coordinates from x1 to xn, and assigns xj. So it's also a smooth function on U, so we can apply vector fields to it. Okay. And so we also recall that we do have a local basis for this set of sections, that local basis of lambda p m restricted to U is given by wedge products of these base elements. So dxj1 wedge dxjp, and we just order them such that they're in increasing order, and there is no repetition, because we know if there is a repetition, they're just 0. Okay, so this is also a basis for this set of sections. And now the theorem, which maybe is a bit long, so I'm going to use the next page. We take a manifold M. Then there exists a unique R linear operator. Operators, technically, operators, which we call D. Technically, I should call it dP because the domain is different every time, but it's common to drop the P. So this goes from P forms to P plus 1 forms. So that's why I'm saying it shouldn't be just D, it should be like dP. This is usually skipped. So if you take the differential of a function and you apply it to a vector field, then this is the same as applying the vector field to the function. This is true for every f which is smooth on M. And observe that just smooth functions on M is simply the 0 forms. So when you take this external product and instead of P you put 0, what you mean is kind of like an empty product. So you just think that this is the trivial bundle. And sections of the trivial bundles are simply smooth functions. And V, of course, needs to be a smooth section of the M, so a vector field. Then we ask that if you take the wedge product of two forms, and then what you get is some sort of Leibniz looking rule with a sign. So the standard Leibniz rule here has just a plus. This -1 to the P does not appear. But here we have this -1 to P. And of course, I have to tell you what P is. So omega is a P form. And omega prime is some Q form. So we know that if we take the wedge product of omega and omega prime, this is a P plus Q form. And if you take differential, then this should be a P plus Q plus 1. So here we get the P plus 1 plus Q. And then you got the P plus Q plus 1. And then the last condition, which is perhaps, I don't want to say it's the most important, but it's really useful and relevant, is that if you compose to this, and this is usually denoted by d squared, even if technically this is not d squared, but these are two different maps. This is dp composed dp plus 1, but just denoted by d squared, then this is 0. So it's the 0 operator. It sends any form to the 0 form. Okay. So have you seen this theorem before? Yeah. Okay, therefore we can skip the proof. It is mostly computations, but they're not stupid computations. You do really have to use, it's not just, okay, I compute and it turns out that this is unique. You do have to use some facts about, okay, of course you have to use these three properties, otherwise there's nowhere to go. And you do have to use the how this base is cooked up, and the fact that when you switched two elements, I mean, when you switch dxj1 with dxj2, you get a negative sign. So it's not trivial computations, but it is computations. One thing which is not computation is, so just one aspect I want to point out, just one remark about the proof. And it shows that we must show, must is always a big word, but we show that D is a local operator, which meaning that if omega and omega prime are two P forms on M, such that omega restricted to U is the same as omega prime restricted to U, where U is an open subset of M, then the differential of omega restricted to U is the same as the differential of omega prime restricted to U. Okay, so this is what it means to be a local operator. It means that you really only look at what's happening there. It doesn't matter if this omega prime are completely different. That's how you knew they're the same, so they have the same differential in U. Okay, and this you do with some partition of unity. Okay, the proof is very long, so that's why we're going to skip it. I'm going to give you another statement without proof about this differential proposition and manifold omega P form, smooth P form, and then we take V1, P plus 1 vector fields. Then, this is a big formula, probably need 2 lines. P plus 1 factorial times d omega applied to the P plus 1 tuple of vector fields. So remember that, okay, before I tell you the proposition, which is what this is equal to, let's recall what this means. So omega is a P form, d omega is a P plus 1 form, and we know that P forms act on they're alternating multilinear operators on Tm to the P, basically. So that's the definition of this on the PM, yeah? So T star M would be just linear forms, and then you can take just the product of this, and then you have the tensor product, then you have multilinear forms. This is the alternating multilinear forms. So in particular, you can input here this P plus 1 vector fields. And this should give you something. This something should be a number. Or, well, a function. Depends, when do you put P or not. Okay, and what we want to do here is express this thing here with respect to omega and with respect to these omega P's here. These VPs. So here we have a big sum from j equal 1 to P plus 1 of -1 to the j plus 1. And here we have Vj, so a vector field applied to a function, and this function is omega of V1, then you skip Vj, and then you go all the way to Vp plus 1. There's still another part, but let's again examine this part alone. Okay, so this omega is a P form. So if you put P vector fields inside, what you get is a function, right? And these are P because we're skipping Vj. So now it's a function, and to functions, we're going to apply vector fields. So we do it with this Vj. So this is a kind of function. And sum of functions is a function, so this part is good. And then we have the second part, and maybe it didn't take enough space. Then it's the sum for j less than k to p plus 1 of -1 to the j plus k plus 1. And then we have omega. And in the first slot, you put vj, vk Lie bracket. So the Lie bracket between these two. And then you put all the rest, but you have to skip vj and vk. Okay, so again here, we have omega, it's a p form, so I have to input p vectors. So here I'm removing two of them and adding one of them. So these are p. If I apply a p form to p vectors, you get a function. So this is again just a sum of functions. This formula as it is looks very complicated, but it is much simpler if we take omega to be a one form. This is actually easier to remember and very common to use. So if we take the omega of v comma w, what you get is v applied to omega of w minus w applied to omega of v. Oof, my v and omegas are very similar. I'm going to make the v a bit more sharp. W omega. Okay. So maybe we're going to put even more parentheses. And then you put omega of the Lie bracket of v w. Okay. And here we go with no proof as well. So this is a formula which, if you work with differential forms long enough, it's kind of come natural. It's come natural at some point. Okay, so to work a bit more with forms, let's define the pullback of a form. We have two manifolds, and we have a smooth function between them. The pullback f tilde, f star, f upper star. Careful, because some authors use f lower star for something else. So it's important that the pullback it's f upper star. The pullback along f, so this is called the pullback along f. It's f star. Is a map from p forms on n to p forms on m. So it's the other way. Pull back, right? Yes, pulling back. That takes omega and sends it to f star of omega. So I have to tell you what is this f star of omega. And well, this is a p form. I mean, I'm giving that it's a p form. So I have to make it act on p vector fields on m. And I'm also going to give a point this time. So remember, this is if I apply it to p vector fields, this is a function, but I also want to give it a point, so x. And this is defined as the form omega at the point f of x applied to the vectors dfx v1, dfx vp. Okay, so for x in n, oh yeah, x in m and v1 vp vector fields. n. Okay. So again, everything makes sense. Let's just verify that because these are, so I'm promising that this is a P form on M. So I have to apply it to this vector fields. And when I do, now I have a form on N at a point which is on N because f of x is in N. And I have to apply it now to P vector fields on N. And these vector fields are like what is sometimes called the push forward of these vector fields. And this is the one that sometimes, so I use red. This is the one that sometimes is denoted by F star of VP, the push forward. So the top one is the pull back, the bottom one is push forward. But I'm not really familiar with this notation. I know it's used other ways as well, so I'm never going to use it.
And this satisfies some like the usual picture for the pullback, or is the rain?
Yeah. I'm thinking. It should satisfy some picture, right?
Yeah.
What do you call it? Pullback. I'm gonna just put the lemma first, and then we can discuss about that.
Great.
Because it kind of ends the topic. So the lemma is that this pullback works well with wedge products. Yeah. And it works extra well with differentials. So whenever we see something like this, it means that some diagram commute, yeah? So perhaps we should look, that's why I wanted to say this first. Yeah, I'm gonna put purple just because to emphasize that I'm not looking at notes here, we're just trying things. So well, we have N, M, here we have F star, differentials, right? Like, I mean, that's the one we know commutes, but it's not the one. This is F star again. I'm sorry, this should be +1. So this last part of the lemma is telling us that this diagram commutes. Commutes is sometimes written like this, sometimes like this. I don't know what you prefer. But yeah, usually, I mean, when you think pullback, you want to see something like F, I think. I think what you wanted to see was something like this. I don't know, something here, something
Yeah.
here. You have F star, yeah.
But the problem is also F star is the wrong way
It's
around.
like yeah,
So
exactly. So,
okay.
no, I don't think.
Well, okay.
I'm sure there is some category in which this is a pullback in the categorical sense. But it just makes sense to ask this question. It's the same word and
Yeah, just if I could have some easy way of remembering, but well,
yeah,
I think
sense. Some
it's a
universal
collective.
property.
Yeah, but no.
No, I'm not sure if if this pullback satisfies some universal property. Should. I mean, it feels like it should. Just because it's called pullback, though, I don't see it from the definition for sure.
Well, okay, I can try something out myself
Yeah,
tonight.
let me
So
know if
yeah,
sure.
I will.
Okay, so this lemma also will not prove. This is really just calculation, not fancy calculation, just calculations. Okay, and I think all of us, the first time we see these terms like dx1, dxn, is when we do integration. Yeah, in the integral from 0 to 1 of f of f in dx. And you see this dx and they tell you, don't worry, it's just a symbol. But now we know that it's something more. But these forms that we have, we never, I mean, at this point, it feels they should have something to do with integration. Because why would you use the same symbol? And in fact, they do have something to do with integration. And let's see how that works. So we will write dx1, blah, 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 dxn with the absolute value to denote the Lebesgue measure. Lebesgue measure on Rn. Okay. Now, if we take a subset, an open subset of Rn, Q, and a diffeomorphism psi, from Q onto its image, and we just write Y as the image of this. So I'm just giving names to different coordinates, basically. So Y's are the coordinates on phi of Q, and X are the coordinates on Q. Then for every F, which is smooth, well, technically just integrable, but let's keep it smooth. We have that the integral on phi of Q of f of y in dy. So if we integrate on this set here, is the same as integrating on this set by precomposing phi. But then you have to add the determinant. The absolute value. So with this, of course, I mean the determinant of the Jacobian matrix, yeah? Absolute value. Right? So this is simply the change of variables formula. Should be extremely familiar with it. Used it many, many times. And I want to show you this can be seen as in a slightly different way. So for instance, the set of n forms on our n has dimension 1. Right? In particular, generator is dx1 wedge stretch dx9. In particular, for every n form on our n, there exists a unique smooth function such that omega of x is nothing but f of x times dx1 wedge dxn. So it kind of makes sense to define the integral over Rn of such a omega. So now we're trying to define the integral of a form as the integral of f of x with respect to the Lebesgue measure. Okay. Problem 1, this is not well defined. So let's see why. I mean, it is well defined. The problem is it does not satisfy this formula here. Like it is well defined, but it's not independent of the coordinates. That's okay, to be more precise. So we take phi. Sorry, let. So I want to show you that this is not independent of coordinates. And we just stay in R2. and simply take the map that switches coordinates. This is, of course, the nicest diffeomorphism you'll ever see. I mean, the identity, I guess, is nicer. And just take a form here. Just stop degree. Then this is by definition, yeah, what we just defined, f of y in dy1, dy2. But now we apply our change of variables. So think this R2 as phi of R2. So this is again the integral over 2 of f of phi of x dx1 dx2. And now what I would like to say is that this is the same as what I would like to say is that this is the same as this, but it's not. You got a minus there. Yeah, because you're missing the determinant still. And this switches things, you know, when you take the pullback, this switches x1 and x2. So this is not going to work. So in particular, yeah, so what I was saying before, 2 omega is not independent of the chosen coordinates. Well, we know that the standard integral in R2, it's independent of the coordinates. You know, you only need to know the shape of the domain. And the reason that that's independent is because here we put this absolute value for the determinant, yeah. But of course we do have, I mean, here, what is the problem here? The problem here is in fact that this determinant, this Jacobian, is negative. Right, it's -1. So if actually we have something which is orientation preserving, so if this change of variables is orientation preserving, then we have nothing to worry about. So let's take something with compact support. And for a form to have compact support, it means that this f has compact support. Then we take phi from Rn into Rn, orientation preserving. Which means, again, that the Jacobian of phi is positive everywhere. Then this is actually true. This holds. So in fact, we're independent of coordinates. And the proof, well, the proof we've basically seen it. I mean, yeah, I'm just gonna write a word. The point is that this Jacobian is the same as its absolute value. Oh. So this is simply change of coordinates. Maybe just one more thing about this. Let's see this object in coordinates, because this we never did. No. This is, I mean, if you write it like this is basically f compose phi, then you put this determinant, and here you put dy1 wedge dyn, and y here is this image of phi. Okay, so this is like at the point y, and this is at the point x. Okay. And now, I mean, so when you write this, you're actually writing this. Then you're like, oh, okay, but this is my good old friend because these are the same. Okay. So if we want to define integration of n forms on M, we need to fix an orientation. So we need that M is orientable, so and choose an orientation. It's not enough that it's orientable. We actually have to choose one orientation. And then basically say that the only allowed change of coordinates are the orientation preserving ones. So let's see this more in detail. Like, how do we actually define this integral? So we take a orientable manifold. We take an oriented atlas. Such that U alpha is finite, and each one of them is compactly contained in M. So when we choose an oriented atlas, we're choosing an orientation, yeah. And then we take a partition of unity. For U alpha. So for U alpha means subordinated to U alpha. And we take a top degree form with compact support. And now we finally define what is the integral of this n form. Well, basically we know how to do things in Rn. So we use the partition of unity. And we take the sum over alpha of the integral over phi alpha of U alpha of phi alpha inverse star of the form n alpha omega. So this n alpha omega, you can think about it, eta alpha omega, you can think about it as n form defined only on U alpha, right? So I can apply the pullback, and what I get now, it's a n form on a Rn, on an open subset of Rn. So I can integrate it by the way we defined it before, okay? And the point is that this is well defined now. Because all these change of variables that we have here, all this c alpha -1, they're orientation preserving. So it doesn't matter which one you put and how you put them. You always get the same. Like if you take a different one, it's okay. If you take another atlas which has the same orientation, then this is the same thing. And in particular, we actually get something more interesting, that if you take the set of forms with compact support, then the integral, like applying an integral to a form, it's a linear operator. Yeah, so you can think that it lives in some kind of dual space. And I'm sure you heard about Stokes' theorem back in your analysis 2 days. And you also heard about Gauss-Green and all this other theorem. Was the circuitation one, all these ones, which basically what they do from a geometric point of view is that if you have a full shape, be this a surface with a boundary or a volume with a boundary, you can somehow relate the integral of something on the full thing with the integral of something else on the boundary. These theorems are all the same philosophy. And in fact, they're all corollary what is called the Stokes theorem in geometry. So we take M, be an oriented. Maybe I'm gonna use a different slide. I'm gonna write the same thing, but just in a new one. So theorem Stokes. Let M be an oriented manifold. So oriented means that it's orientable, and I chose an orientation. Boundary. And let I be just the embedding of this boundary in M. Okay, so this is just the thing itself. And now we take compactly supported n-1 form on M, and you get this nice thing, which is the theorem, that if you integrate I star of omega, which observe this is a n-1 form, right, on the boundary of M, which you can just think of omega restricted to the boundary. Just take omega restricted to the boundary. That's really what this is. This is equal to the integral over M of differential of omega. Okay. And if you think back at all those theorems, it was always saying like, oh, the integral of, it was something like the integral of a function over the boundary, it's equal to, I don't know, either the integral, the circuitation, which was something which had to do with the nabla operator. So on the right, when you were integrating on the bigger side, you always have some kind of differential operator. It could have been, yeah, the divergence, it could have been the curl, blah, blah, blah. But all of this are just under here. So basically the divergence, you can think about it as just, I mean, if we're in R3, is the differential of a 2 form. It's basically the divergence of an appropriate vector field. The curl is a differential of a 1 form, etc., etc. The gradient, of course, is just the differential of the function. And well, the idea of proof here is somehow interesting. First of all, we need to reduce ourselves to Cn, to Rn, of course. Yeah, because things are easier in Rn. And to do that, you just apply a partition of unity and local charts. And there, so there, we use a combination of the fundamental theorem of calculus, the theorem of calculus, which is simply the one that says that the integral of the derivative is the function itself, and the Fubini-Tonelli theorem, which means you can exchange order of integration. Yeah. And this exchange, the fact that we use finitely is actually the reason why we need to ask that this omega is compactly supported. Because this exchange order of integration is only valid if you have compact support. Or, there is these other theorems which are also tell you that, if some integral is infinite, then doesn't matter which order you do, it's still infinite. But that's not always the case. So to be safe, you just put compact support. Okay. And this is an interesting corollary for compact manifolds. So without boundary, so just a compact manifold, think of a sphere. And then every form, which is n minus 1, and we have then every form, we have the integral of its differential is 0. Yeah, simply because you apply this, but this is empty, so you get 0. And this is something you already seen for one forms, which basically tells you that if a form is exact, its integral is 0, right? And this is the same. Being exact means being the differential of something. As an exercise, which I think, again, this is one of the interesting exercises, not one of the, we don't have time to do it in class exercises. Prove that M is orientable, because remember, for all of this, we need orientability. If and only if there exists a top degree form, which is never 0. And maybe, okay, so this is the exercise, but on observation, this is also equivalent. So this is an extra if and only if, which is the same as asking that this bundle is trivial. Because remember that this is a dimension 1 bundle. So being trivial is equivalent to having a nowhere 0 section. Okay, so these are the same condition. And it's the same as orientability. Okay. So this concludes the recall for chapter 3. And now it's time to bring out the big guns and talk about cohomology. So the official name for this chapter was the Rhur cohomology, but then I looked about it again, and I think the right name should just be cohomology, and as a subtitle, the Rhur complex. So what I mean by this, we're not just going to do the Rhur cohomology, which you already know. We're going to do cohomology in general, and then see how cohomology in general, how the Rhur complex is a special case of these general facts about cohomology. So I definitely think this is the most interesting part of the course. Not necessarily the most challenging yet.
Maybe just one quick question concerning the exercise. There was an n. Is it the dimension of M, or what was it?
Yeah.
Okay, yeah, good. Thank you.
Of course. So what is cohomology? We start with a family of abelian groups. So now we're switching a bit towards algebra. This is, in fact, the topic is called cohomological algebra. So we just take some abelian groups indexed by natural numbers. And suppose that for every j in n, we have a map that goes from one into the next. and these are group morphisms. And we say that the sequence V1 goes into V2, goes into V3, etc., and here the maps, of course, are alpha 1, alpha 2, 3, etc., is a cohomological complex if you apply two of them successively, you get 0 for every j. So the takeaway message here from this thing here is just telling you that the image, if and only if, image of alpha j is contained into the kernel alpha j plus 1. I think this is the take-home message from this. And we also say that the cohomological complex is exact when this is not an inclusion but an equality. Okay. One second. Okay. And let's just look at the few observation. Every time we have an exact sequence, it's important to look at zeros. So for instance, if we have 0 goes into V1 and then we have alpha 1 and then blah, blah, blah is exact, then what this means is that alpha 1 is injective. And vice versa, I mean, not really vice versa, but if at some point one of them is 0, sorry, not one of them is 0, but they're all 0 from some point on, then alpha j0 minus 1 is surjective. So the previous one. Okay.
I guess it's enough if one is 0, right? But okay.
Yeah, I was also thinking the same, but I think here we're not asking exactness anymore. Like this is true even if the sequence is not exact, if it's just a cohomological complex. I think.
Okay.
Maybe, let me think about that before. If it's exact, of course, as soon as you have a 0, then the previous map, it's, yeah, it's here, if we have surjectiveness, so we have a cohomological complex like this, and then at some point on some are 0.
Yeah, that doesn't really
Yeah.
tell us anything because we don't know whether the image could be much smaller than the kernel of the next function. So I think we need exactness.
But then we're asking too much here, right?
Yeah.
Yeah, as I was writing, I was a bit, wait. Are we sure? I just want to think again about this.
Sure.
What if we only take a cohomological complex? Again, at some point there's 0, so this map is 0. Yeah, this could have already been 0, right? No questions asked. Yeah, okay. I mean, this I definitely agree. If one is 0, then the previous one must have been surjective. Yeah. And okay, one other thing, which is an exercise, which is very easy. is that if you get more zeros in between, so again, we have an exact sequence. I mean, it doesn't need to start with 0, just an exact sequence. And if you get the Vj minus 1 and Vj plus 2 are 0, then the two in-betweens are isomorphic. This should be very easy. Just say some kernels, some images are the same. And so when we have a cohomological complex, one thing we can do is define a cohomology. So given the cohomological complex V dot a dot. So this is going to be standard from now on to denote the sequence. Yeah, we just write like this. And the first time I saw it, I expected this to be a J, but it's just common to put a dot. I don't really know why. So we define the cohomology of the complex. Homology of the complex is HP to the top. So P, the top is reserved for cohomologies. The bottom is reserved for homologies, which are something similar, but basically goes in the opposite direction. They're like one the dual to each other, but we'll only do cohomologies here. So for the first step, it's simply the kernel of the first one. And otherwise, you take the quotient kernel modulus image. Yeah, and this is allowed because as we've seen before, the image is contained in the kernel, so we can take this quotient. And these are abelian groups, so we don't have to think about normality or anything. They're just quotients of groups. So once we have new objects, cohomologies in this case, cohomological complexes in this case, we're interested in morphisms between these objects because categories have lots of nice properties. So let's take two cohomological complexes, A alpha, B beta, cohom complexes, and a morphism between them is a family. Phi dot again of group morphisms such that now we take a very categorical looking approach by doing diagrams. If this is commutative. For all J. Yeah. So, just think that you have one complex here, is A here, and you have the other one here, B, and you just map level by level, but you can take all possible directions. So quite intuitive. And the cool thing here, that since these are group morphisms and everything commutes, is that a morphism of complexes, homological complexes, induces morphism between cohomologies, which you still use phi, but now we use the p above. And this go in the right direction. This is a b, this is a beta. Okay, so to do this, so I'm gonna put exercise, verify the statement. Yeah, but of course, I mean, I think the idea should be very clear. It's more an exercise about chasing diagrams. This is actually a proof technique, which is called diagram chasing, which I find the first time I saw it, I found it quite beautiful. Even if very hard to write down. And this is like a first small exercise in this technique. Okay. So now that we have objects and morphisms between them, we can define exact sequences. So we have a cohomological complex that goes into another cohomological complex that goes into another cohomological complex. So this is a sequence of cohomological complexes is exact if it is exact at every level. Yeah, we know what exact means for group morphisms, and of course these are these maps that I have here are map morphisms between cohomological complexes. Yeah, so diagrams come up tonight. And exercise, and this is actually a really interesting exercise, I would say. Proof that the induced maps in cohomology So we have a map. I mean, just think here we have a map between the complex A and B. So this induces something in the respective cohomologies. And here we have another map, which induces something in the respective cohomology. Give an exact sequence, which is not a short exact sequence in the sense that it's missing the zeros.
So this is more or less the snake lemma, or?
Oh no, you know it. Okay, that was
So
the.
I actually have a mug, but now it's in the dishwasher. I will bring it next week.
You have a
I
what?
have a
With
mug
snakes.
with a snake lemma.
Okay. Okay, then maybe we will skip the proof of the snake lemma. We will recall it. I mean, you know it, like you saw the proof.
Yeah.
Okay, we will definitely recall it. Then maybe, I mean, the plan was to stop here, but since we're skipping the proof, I'll just recall it.
Okay, great.
So yeah, the snake lemma is basically telling you what's missing here. Yeah. Snakes lemma. Is it gonna fit here? Yeah, it exists. Okay, so we start with a short exact sequence in cohomological complexes. Be short, exact sequence of cohomological complexes, then there exists a long exact sequence in cohomology. And the exact sequence is this one. So you have the cohomology of A. Then you use the standard map here, the induced map. Again, here use just induced map, so nothing fancy. Let's say this part we know is exact. So I mean, when you have just three things, being exact is really a proposition about what's in the middle, yeah? So on this point we're exact, and here we put this map, which is the one given by this snake's lemma. So this is the important one. This is the one we need to build, because this one lets you go up in cohomology. Sorry, it's just a dot. And then here you continue with phi p plus 1, etc., etc. So now you restart. So here on the left, this would be delta p minus 1. Yeah, that's how you go up. So yeah, the idea of, I mean, the main part of the proof is to build this map here, this delta. And yeah, it's, I think, the most extensive use of diagram chasing I did in my life. But yeah, since you're already in the proof, we'll skip it. And if you have some questions about it, you can, I mean, if you want to see it again, you can write me, we can do it separately, or, you know, you can just find it on any book, or I'm pretty sure you can just find the video as well. Okay. Yeah, I think this is a good place to stop. And next time we will talk about the Durham complex. Okay, so we will kind of mix everything we did today. So we talked about this P forms, yeah. And here we already imagine, see, we have groups with maps that go up, and we have this condition. So we already know we have this cohomological complex. We already know that the RAM complex is a cohomological complex. And so we kind of expect that its cohomology will be interesting. You know? And the respective induced maps of given from the pullback will do something, etc., etc. So that's for next time, and that's it for today.